Thank you, Mr. Davidai. That was indeed informative sharing. Thank you. And now we have reached the last session of the day, and I would like to introduce our old friend, Mr. Philip from the FreeBSD Foundation. His topic is called the ZFS, which it is known as the last word in file systems. This workshop will get your hands dirty with installing, configuring, and managing reliable and scalable storage systems with ZFS on FreeBSD. We will cover pool-based storage, optimizing storage systems for performance and redundancy, and practicing zero downtime recovery from common storage events, such as falling disk or running out of space. Now, may I pass the time to Mr. Philip.
Thank you. I think this is the first time I give this presentation in a completely empty room. I would like to thank the few people who are in this room to be here to make this slightly less weird. As you can see from the opening slide, this is actually a one-day workshop. That's also a lie. It originally started as a 3-day workshop, and then I was asked to trim it down to 1 day. And then earlier this year, I gave this presentation at LinuxConf Australia, and had to fit in 45 minutes. And now here we are. The world has broken a bit, and I only get half an hour for this 3-day workshop. So let's dive into it. Short history of ZFS. ZFS is a bit, well, it's almost old enough to vote in all of the world. It started in 2001 at Sun Microsystems, which no longer exists. It's now called Oracle. About 4 years later, they released the source code as open source, which was really nice of them. FreeBSD took 3 years to pick up the open source code drop and integrate it with FreeBSD 7 around about 2008. And the last line of this slide keeps changing. Currently, FreeBSD ZFS is reported to work reliably on Linux as well. So if you don't have access to a FreeBSD machine for whatever reason, you should just go and install FreeBSD. But if you don't want to do that, you can do all of these things on Linux as well using ZFS on Linux, or as it's now known, OpenZFS. This is now supported in many distributions. So what is ZFS? Well, first of all, ZFS is a file system, but it's not just a file system, it's a file system and a volume manager. So it allows you to take care of your storage in one system, rather than having a volume manager separate from your file system. And it provides 4 key things to your storage needs. First of all, it gives you end-to-end data integrity. Which means it detects and corrects silent data corruption for you. A hard disk's joy in life is eating data. When you store a file on a hard disk, you're not actually keeping it safe, you're feeding it to the hard disk. The ZFS provides pooled storage, so it's a 128-bit file system. It just skipped the whole 32-bit, 64-bit stuff and went straight for 128 bits. More bits, more better. And the pooled storage also eliminates the antique notion of volumes. Historically, when you had a non-trivial storage requirement, you would have to take your hard disks and then add volumes on top of them. So you'd have to think about, you'd have to basically predict the future. How much space will I need for the stuff that I'm about to store? And you call that a volume, and then inevitably, after a while, you go and run out of space, and you need to expand the volume, and this is terribly painful and fraught with perils. ZFS takes care of all of that for you by making the pools automatically expand to fill all available disk space. We'll see more on that later. ZFS also implements a transactional design, which means that your data is always consistent on disk. There is almost no way to corrupt data in ZFS. If the blocks hit the disk, the file system is going to be consistent. If you hit a power failure at an unfortunate moment, your file system is not going to blow up on you. There's no FSCK in ZFS. All the data are always consistent. And as a bonus, as part of the transactional design, you also get huge performance wins because of the way it's implemented by copy on write. Finally, ZFS provides simple administration. Usually, when I'm presenting this talk in the real world, I would ask who has ever resized a file system on Linux, and who has enjoyed the experience, and the number of hands, all of the hands go up, and then all of them go down. ZFS has 2 commands in total to manage your entire file system. There's no FSCK, there's no new FS, there's no make FS, there's no tune FS. None of that exists, no check disk. Just 2 simple commands to manage your pool and your file systems on top of them. So let's dig into these things a little bit deeper. First of all, the first thing I mentioned is end-to-end integrity. Here's a list of things that can fail in any storage solution. So the disks are the obvious ones. Disks are little monsters, and eventually they get tired and they die. And that's just the first thing that can go wrong. Disk controllers can go wrong. The people who write firmware for disk controllers can be wrong. Cables mysteriously rot, no matter what the climate conditions in your data centers. Eventually you're going to have a cable that loses its tiny little mind. Device drivers are written by terrible people. I'm a device driver author. And non-ECC memory will mysteriously get bit flips from time to time, and what you wrote will not be what you thought you wrote. So all of these things can fail, and most file systems implement disk block checksums to protect you against at least some of these failures, but what they actually protect you against are just bit rot, because in traditional file system design, your checksums are stored with the data blocks. So any self-consistent block will have a correct checksum. Hooray, great. But if you had a stray write, or if you had a misdirected write, or any of a number of device driver bugs or accidental overwrite, what you're going to have is your data block is going to be written, and its checksum is going to be correct, and your file system is going to be happy. So that's not very good. Your disk block checksums in traditional file system designs really only protect you from bit rot, and they only validate that your media is mostly working. It doesn't protect you from any of a million other things that can go wrong with file systems, or with the things you run your file system on, rather. ZFS takes a completely different approach. ZFS stores its checksums in the parent block pointers rather than with the data blocks, which provides fault isolation between the data and the checksum. And the entire storage pool is actually a self-validating Merkle tree. If you've ever used Git, it's the same data structure, more or less. And this allows ZFS to give you data authentication, and it allows ZFS to validate the entire I/O path. So bit rot is just one of the things ZFS will protect you against. It'll also deal with phantom writes. If something's been written to the file system which the file system isn't aware of, or something's been written to the disk, rather, which the file system is unaware of, ZFS will go, hey, this is wrong, we didn't expect this, your disk is lying to you, or your cable has rotted away, or something has nibbled at your bits, go and replace that disk. We'll see a little bit later in this talk how that works in practice. So that's the integrity story of ZFS. I'm rushing through this because I want to get to the fun bits. Another cool feature of ZFS is your pooled storage. So this is what a file system or a storage architecture looked like in the 90s and the early 2000s, and basically before ZFS existed. You have a single partition or a single volume per file system. So you have a disk, and there's a file system sitting on top of it. And each of these file systems has limited I/O bandwidth, and your file systems have to be manually resized. If you add a disk, you need to resize your volume, you need to resize your file system, and your storage gets fragmented over time. So if you have a concat, for instance, or a stripe, if you like, you'll have 2 disks, and then you have a volume sitting on top of that, and a file system sitting on top of that. If you want to add a disk, you need to recreate the volume, and then you need to expand the size of the file system to fit the new volume. And this is the same no matter what the underlying storage technology is. ZFS makes this a lot smarter. There's no partitions in ZFS. ZFS just uses the raw disk. You add disks to a storage pool, and then you stick ZFS on top of that. So all of the storage in the pool is shared. The file system doesn't actually know or care which disk it hits, or or where it is stored. The storage pool abstracts all of that for you, and the storage pool is self-managing. So if you add a disk to the storage pool, it grows. If you take a disk away, of course, it blows up. Don't do that. But as a side effect of this pooled storage design, all of your I/O bandwidth is always available. You don't have this fragmented setup where you have to have a file system and then a volume and then your disks underneath it, and then you go and create a new volume, and then you only have the I/O of that volume. So you don't have to pre-think your storage architecture. You can just, the pool will grow automatically, and all of your bandwidth will always be available. Thirdly was your reliability, the reliability of the file system and the impossibility of becoming corrupt. ZFS is designed as a copy-on-write file system, which means that it writes the data blocks first, and then when it's written the data blocks to the disk, and the disk has told it, the blocks are really there, it's cool now, it goes and updates the pointer to the blocks. Once that's succeeded, it goes and updates the pointer to that block. And only finally, when all of the data blocks and the intermediate blocks have been written, does ZFS go and update what it calls the Uber block in one atomic operation. So at no point, if the power fails in any of state 1, state 2, state 3, or 4, at none of these states can you lose data or can your file system become corrupt. The only thing you can lose, of course, is the newly written data. So if you unplug the power before the Uber block has been updated, you're going to lose those last 2 data blocks, but you're not going to have file system corruption, and you're not going to lose access to any previously written data. Finally, the fourth great advantage of ZFS is that you can throw away all of these wonderful commands which you know and hate. You can throw away fsck, newfs, makefs, mount. You can throw that away. You can forget everything you know about the ZFS tab file because it is no longer relevant. You manage your ZFS storage system with exactly 2 commands. You have zpool, which adds and replaces disks. You resize pools with it if you manually need to do that. And you have the ZFS command, which manages file systems. So on a higher level, you can manage quotas, reservation, compression, deduplication, snapshots, clones, all of that stuff. And this is where I stop poking at slides and I start poking at xterms. This is traditionally where projectors get cranky at me. Oh, good, it hasn't blown up. Somewhere on this system, I have a terminal. Oh. Maybe I can actually get to my virtual machine. All right. Did I misspell tank? There we go, I misspelled tank like that. It's gone. I said earlier in this presentation that ZFS completely abstracts your notion of volumes. If you have more than one disk, you can just add them to the pool. So imagine, I'll spell tank correctly this time. Imagine I went to the shop and I have 2 disks. I'll just go and create them dev md1. If I do this command, I'll create a pool called tank with the 2 disks I went out and shopped for. If we list the pool, indeed, we now have this tank with about 4 gigabytes of space. ZFS, like every other file system, eats a little bit of space for metadata and journaling and all of its good stuff in there. So this is not very good, though. So what I've done now is I've created the moral equivalent of a concatenated volume. All of the data will be written on disk 1. When disk 1 is full, it'll end up on disk 2. That's not very good, or well, that's not terribly useful. So let's destroy this again. By the way, you might have noticed how quickly zpools get destroyed. Destroy is just a constant time operation. ZFS is a file system for adults. There are no seat belts. If you type ZFS zpool destroy, your data are destroyed, and there's no questions asked. So that's, that was a concat. If I wanted to create a mirror, I don't need to go and look on the documentation how to do that, because the 2 commands that ZFS provides, zpool and ZFS, are actually very friendly to use. So creating a concat was just doing this, zpool, dear ZFS, please create me a pool called tank of these 2 disks. If I want to create a mirror, I just do the same thing. Dear ZFS, please create me a pool of 2 mirrored disks called MD0 and MD1. There we go, I now have a pool. How much space will I have on this pool? Well, it'll be half the total, or the space of one disk. So I go and list it again. There we go. Indeed, I have about 2 gigabytes, which is the space of one disk. I'll automatically get a file system on this, and ZFS will mount that file system for me. If I type mount, it'll end up at the bottom. There we go. ZFS is a very friendly file system. On top of this pool, it's created a file system with the same name as the pool called /tank. How much space have I got? Indeed, the numbers never add up because Unix numbers are hard. It automatically mounted this file system. I didn't have to add anything to its ZFS tab. I didn't have to type mount. I didn't have to do anything magical there. And now this is a mirror. So if I write to this file system, I'll have 2 copies of the file, one on disk 0 and one on disk 1. That's all. That's disk 2. Two, 3, how many did I create? 5, 4, 5. I've bought some disks, plugged them in. Now I'll go and create my pool, and instead of a mirror, what I'll do is I'll create a RAID Z set. There we go. MD2, MD3, MD4, and MD5. There we go. Z pool list. Now this tank here. Now the tank has 11 gigabytes. All of the storage, of course, is virtual. None of these disks exist. They're just empty files, and I've created loopback file systems on them. But these 11.5 gigabytes are striped across these 5 disks I've created. If I lose one of those disks, the file system will be happy. How do I lose one of these disks? Well, I can go and write some garbage over them. Is one way I could lose disks, or I could unplug it, or I could do any sort of terrible thing to it. If I lose one of the disks, the file system will keep existing and will keep working. If I lose 2 of the disks, the file system will be toast. So ZFS provides another container for file systems that need more reliability. And again, all of this is managing the storage for you. So I'll just destroy this pool again, because I like destroying pools. If I change the RAID Zs to RAID Z2, I can now lose 2 disks and the file system is happy. Finally, RAID Z3, I could lose 3 disks. And I have 10 minutes left in this 3-day workshop. Hopefully I'm enticing you to go and download my slide deck and play with ZFS yourself. If you download FreeBSD, you don't need to do anything else. This virtual machine was created several minutes ago. Precisely for this tutorial, I didn't install anything other than just the latest version of FreeBSD. If you're doing this on Linux, you'll need to install OpenZFS and maybe play around with several kernel modules before you can get ZFS working. On FreeBSD, it'll just work for you. Let's just look at this pool I've created and do a little bit of playing with file systems. So zpool lists your pool storage, and zpool is not a very exciting command. It allows you to add disks, remove disks, and configure how your storage pool is set up. ZFS is a much more interesting command. It allows you to create file systems on top of your pool. So as I said earlier, ZFS automatically creates a file system for you on top of your pool, named the same as your pool. If you wanted to create a new file system, again, it's a very simple command. ZFS creates tank/stuff. I can't even spell stuff today. There we go, tank stuff. I've now created a file system called stuff on top of tank. If I do mount, you'll find that it's automatically mounted this file system on /tank/stuff. But that's not where I want my stuff to be. I would like to have my stuff mounted somewhere else. And all of this is obviously documented in a manual, but you can just guess most of the commands. If I wanted my stuff to be mounted elsewhere, I can say my mount point is /mumble, let's call it /mumble tank/stuff. And if I look at mount now, ZFS has done what I wanted. ZFS has gone and mounted tank stuff on /mumble. I didn't have to go and update its ZFS tab. I didn't have to unmount it from tank stuff and then mount it again on /mumble. It's done it all for me. Other fun features of ZFS are compression. If you want to turn on compression on any other volume manager or other file system, you need to go and grub around in the manual page. If you've played with ZFS for any more than 5 minutes, you'll find that just guessing the commands is going to make it work. If you want to enable compression, you just ZFS set compression on say, tank, and this is now compressed. If I write a gigabyte to this file, or if I write some data, the file system is going to compress it for me at the block level. And it's going to start compressing from that point on. So all the data that were on the file system before are obviously not going to be compressed for you in the background, but any new data you write will be compressed. Properties on ZFS file system are inherited. So I've just set compression on tank, but if I ZFS get compression on tank stuff, you'll find that compression is on for the child file system as well, because properties are inherited on ZFS. And these inheritance properties also apply to more fancy things like quotas and reservations, which you'll find further on in the slide deck, which you can go and play with. With the inherited properties, you can set up really interesting storage solutions for your users. You know, you put your users in their own hierarchies, and you say, right, this group of users has a quota of 5 gigabytes. Anyone whose home file system is in this tree will have that quota. If you have some users who need more space, like the boss for his videos, you put them in another group, and they will have a larger quota. And you can obviously override the quotas or compression or other properties on a per file system basis. ZFS, the last thing I have time for, I think I have another 5 minutes. The last thing I have time for is ZFS has snapshots, and snapshots are really quick. And the command to access them is called ZFS snap. ZFS snap tank stuff. Now I've created a snapshot of the stuff file system, and it was instant. There was no thinking about it. So anything that happens now, if I touch a file, it was mounted on Mumble, call it Wibble. I've touched this file. This file only exists after the now snapshot was created. I can go and look at this snapshot by magic. So if I go into /mumble ILS, there's nothing here except this Wibble file I created. There's no hidden files here either, but ZFS provides sneakily a .zfs directory. Oops, spell it right. That directory is not listed when you do ls, but it exists. And under there, you've got a snapshot directory. You can go and list it here. The now snapshots, whoops, can't spell now. The now snapshots does not have the Wibble file. If I create a new snapshot called later, there we go. I'll go back. The later snapshots will have it. There we go. The later snapshot has it. I can now go and delete it again. Which file? There we go. I've deleted it. It still exists in later. It doesn't exist in now, and it doesn't exist in the file system itself. And I have 5 minutes to go. I would now usually go and break for questions, but I don't have time for questions. Or, well, I have lots of time for questions, but I have no people to ask them. So I'll leave you with a quick browse through these slides. I have lots of worked examples here of working with data sets and creating file systems, mounting things, setting properties. You can find these slides probably on the Hong Kong OSCON webpage, or I'll put them somewhere else and make the Hong Kong OSCON people send you a pointer to them. I strongly encourage everyone to go and play with this. It'll make your storage life a lot easier. There's two kinds of people in the world, those who have lost data and those who are about to lose data. Go and play with ZFS and you can put off your losing data for maybe a couple of months of your life. And with that, I'll stop this talk. Have fun.